In this video, I'm going to talk about internal loadings. So imagine we have a beam here, or a rod, and I told you it's made out of steel. And it's a very long, thick beam, and I just stood on top of it. You would expect the beam to hold, right? What if I made it out of wood? And I said, okay, now to stand on top of it. Stand on the end of the beam. You would say, okay, it's probably going to hold, but you wouldn't know any of the internal damage caused in the wood. We need to make sure that our material that we choose can resist any of the loading acting along the beam. And we need to make sure it can resist it by analyzing its internal loadings. So what are internal loadings? Internal loadings are forces acting within the member, not on it like a point force or distributive force, within the material. So in summary, we have a cutting force in our shear force, denoted with V, that is tangent to the cross-section. We have our normal forces, denoted with N, that are parallel to the cross-section, kind of like a pulling force, pulling/pushing, right? And then we have our bending moment, which is, of course, bending force, bending/curling. Now, basically, to find these forces, you need to find a point of interest and make a cut. And you need to look internally in the beam here. So let's pretend we make a cut like this through the beam. And we're going to look at the left side of the cut here, so this part of the beam. So let's erase everything. So looking at the left side of the beam, we've made a cut at A. And remember the internal forces that I talked about. We have a shear force, a normal force, and a bending moment. So our cutting force, our pulling or pushing force, and our bending or curling force here are called internal forces, and we've made a cut. So how do they look in a free body diagram? So our cutting force, right, pretend that you cut the beam down with scissors, right, is going to be downwards, like this. Our pulling force, remember if we were grabbing the end of the beam and pulling it, is outwards like this. And then our bending force, which is our moment, creates a concavity and bends the beam inwards, right? So this is let's label this. So we have bending moment, we have our normal force here, and then we have our shear force here. Now, let's figure out what makes shear forces or normal forces or bending moments positive or negative. So here's another diagram I drew. We have our beam here, and we've made a cut on either side. This just represents when our shear forces, normal forces, or bending moments are positive. So as you can see, we made a cut on the right side of the beam here. So we put our shear force acting downwards, and you would say that's not positive, that's negative because it's acting downwards. Well, when shear force is positive, so I'm going to put, when V is positive, it's acting clockwise. And then we have our normal force here. When our normal force is positive, it's acting as a tension force, a tensile force. It's pulling the beam. So pulling / tensile force. And when our moment is positive, our bending moment here, it's bending the beam upwards. It's making it concave upwards, right? It's going to end up looking kind of like a bowl. So I'm going to write concave up, and then it looks like this, right? Our beam is going to end up being like this, and then concave down would be positive. So pulling is positive, and then so we had a beam clockwise is positive for our shear forces. Now, knowing all this, let's get into an example. So this example says find the internal loadings at the points, and those points are C and D. So remember we said we had to make a cut to find the internal loadings? Well, first we actually need to do our equations of equilibrium to find our reaction forces at point A, which is a pin connection, and point B, which is a roller here. So let's replace our support reactions, or our supports here, with their respective reactions. So here's our free body diagram. Now let's use our equations of equilibrium to figure out our forces. So now that we have our free body diagram drawn, and we've reduced our supports into their reactions, we can use the equilibrium equations to find our unknowns. We can't go right into, the sum of y forces, because we are going to get two unknowns, ay and by. So let's start with our moment equation. So the sum of moments about A are equal to 0, and let's make clockwise positive. Since we are taking the moment at A, and the moment is equal to force times the perpendicular distance, right? If we're already at A, we're not going to include A. So not including A, we move on, going down the beam, and we run into a force that's 8 kilonewtons. 8 kilonewton force, 8 meters from A, so that means we have 8 force times distance, which is 8 meters to A. So 8 times 8 here. Let's write in the units, times 8 meters. And we are rotating our beam this way about A, so that's clockwise, so it's positive. Let's move along, nothing at point D, move along, and then finally, right at the end of our beam here, we have two forces here. We have a upwards force at B that's causing a negative moment here. So minus the force By times the distance to A. What is the distance to A? Well, it's 8 times 3, so it's 24. Meters. And then we also have a moment right on the end of our beam, so let's remember we don't need to multiply it by the distance, because it's not, it's not like a point load or anything. It's already a moment, and it's going in the negative direction, so that's minus our moment here, 40 kilonewtons times meters. Now all we need to do is solve for By. So solving for By, we have 24 By on the left side. I just moved that over. And then on the right side, we have 8 kilonewtons times 8 meters, which is 64 kilonewtons times meters minus 40 kilonewtons times meters. So minus 40, that's 24. And then solving for By, we get that our force By is 1 kilonewton. Right, 24 divided by 24, 1 kilonewton. Great. Now let's erase this. Okay, now that we know By, let's get rid of it on our diagram and change it to 1 kilonewton. We can just use the sum of the forces in the y direction to solve for Ay. But first, let's realize that the sum of the forces in the x direction equal to 0, and also that Ax is equal to 0 because it's our only force in the x direction. So we can just get rid of that. So the sum of the forces in the y direction are equal to 0. Upwards is positive. 0 is equal to, we have Ay is positive minus our 8 kilonewton point load. Move on, nothing at D, and then at B, we have our positive 1 kilonewton point load. So solving for Ay is equal to, we have negative 8 plus 1 is negative 7. Move that over to the other side, and that's positive 7 kilonewtons. So we have figured out that By is 1 kilonewton and Ay is 7 kilonewtons. Now let's replace them on our free body diagram here. Okay, now we have done it. We have figured out all of the forces that were unknown on our beam here. And now we can make our cuts at C and D to find the internal loadings. Because remember, if we scroll up here to our question, we want to find the internal loadings at the points C and D. So, first things first, let's make a cut at C. Let's make an imaginary cut right in front of C. Very close to C, but just a little bit past it. So we actually include our 8 kilonewton force at C. Right at the end here at A, we have our 7 kilonewton point force. And then we also have a downwards force at C, downwards point force at C of 8 kilonewtons. And now let's draw our internal loadings. So let's single this out. Now, if we remember from earlier, we have 3 internal loadings that we're concerned about, and that's the shear force, the normal force, and the bending moment. And we want to assume that these are positive. So the shear force is positive when it's creating the beam to rotate, when it's causing the beam to rotate clockwise. Our normal force is positive when it's causing a tensile or tension force on the beam, pulling it, right? And our bending moment is positive when it's curling the beam upwards. So let's draw them in. So first of all, at C here, we have a positive shear force downwards, and then we have a pulling force called the normal force. And then, of course, we have our bending moment curling our beam upwards. So now, it's exactly what it looks like. You use the equilibrium equations again, but you do it about point C. So applying the equations of equilibrium at this segment, this is segment A to C, right? We get that the sum of the x forces equal to 0. And we realize there's only one x force, and that's our normal force at C, right? I'm going to change that to C. Let's not confuse anybody. There's only a normal force acting in the x direction. So our normal force is equal to 0. And you might find in a lot of these problems that the normal force is equal to 0. And let's get rid of that. So let's take it off our diagram. So now let's take the sum of the forces in the y direction are equal to 0. So 0 is equal to, we have a force going upwards at A, so that's positive 7, and then downwards at C, so minus 8. And then we have our shear force VC at C as well. Now, you remember when I said that for a shear force to be positive, it needs to be rotating the beam clockwise, right? That doesn't mean you make it positive in your equations of equilibrium. In your equations of equilibrium, it's going downwards, and we've specified that our positive's upwards, so we put it in as negative VC in our equations of equilibrium. And I'm going to show you how this works. So let's solve for our shear force. So VC is equal to, so we're putting that on the other side, right? Now it's positive. 7 minus 8. 7 minus 8 is negative 1. So negative 1 kilonewtons. So all that means is that our assumption that it's acting in the downwards direction at C, it's cutting downwards on it, is wrong, and that it's actually acting upwards. So now let's find our bending moment. We take the moments about C, and let's take counterclockwise to be positive this time. That looks too big. So we actually include our bending moment. Don't be confused by the fact that we took the moments about C. We include our internal bending moment here. We don't include the moment at C, but we include our internal bending moment at C. So that's MC. That's our unknown, actually. And then what else do we have here? MC is going in our positive direction, right? So we also have a force of 8 kilonewtons, but it's directly on C, right? So we don't use it. It's 0 meters from C, so 8 times 0 is 0, so we don't care about that. Next, we have our 7 kilonewton force at A here, and that's 8 meters from C, and it's causing our beam to rotate in the clockwise direction, so it's negative in our case. So minus 7 times the distance, 8. So solving for MC now, we get that the bending moment is equal to 7 times 8, which is equal to 56. 56 kilonewtons times meters. So let's erase everything. Our internal forces at C are our bending moment, shear force, and normal force. Our bending moment is 56 kilonewtons times meters. Our shear force, which is our cutting force, is negative 1 kilonewtons. And our normal force, which is our pulling or pushing force, is actually 0. There is none. So now we need to do the exact same thing, but for D. Now we want to do it at D. So right here. And that leaves us with segment DB, or BD, whichever way you want to do it. And that's 8 meters long, and that has forces, it has a moment of 40 kilonewtons, and it has a force from B of 1 kilonewton. So let's draw that cut. So here's our cut. Remember, it was like that. And we had nothing at D, but at B, we had a 1 kilonewton force in the upwards direction. And we actually had a moment of 40 kilonewtons times meters as well. So there is actually no unknowns. So we can go right into solving for our internal forces. So first things first, let's draw them in. Be straight, please. So first things first, let's draw them in. We have our normal force pulling our beam. And now, since we're on the other side of the beam, we're drawing our shear force upwards instead of downwards. Remember that we always assume it to be positive. And for it to be positive, it needs to be rotating this beam, this segment, in a clockwise direction. So VD, ND, and same thing with our moment here. We need to be assuming that it's positive. So it's rotating, or it's curling or bending our beam upwards. So MD. Now, let's do the sum of the forces in the x direction. In the top here, sum of Fx is equal to 0. We already know nd is equal to 0. We don't even need to spend any time on this. There's no other x forces, so of course our normal force is equal to 0. That is not always the case, by the way, but for a lot of the problems it kind of is. Kind of like how ax is always 0 in these problems we do. Now let's solve for our shear force and our bending moment. First, we take the sum of the forces in the y direction are equal to 0. And we say that 0 is equal to, what do we have here? We have our shear force in the positive y direction, so Vd. And we also have plus 1 kilonewton, our point force at B from our reactions earlier. So we find that Vd is equal to negative 1 kilonewtons. So again, it being negative means our assumption is wrong and it's actually going downwards. Remember that when we did it for the other segment. Up here actually, we also got negative 1. So they're flip-flopped. That's okay. Now that we have this, we can solve for our moment. So Vd is equal to negative 1. Nd, which is erased off our diagram, is equal to 0. And the sum of the moments at D are equal to 0. And let's make counterclockwise positive again. Remember, don't include the moment at D, but include its internal moment at D. So the internal moment at D is denoted as md. And that's positive, or sorry, that's negative. So negative md, because we are actually going, what I call, like against the grain, we're going clockwise, so negative md, and then we have a moment going counterclockwise at the end here, b, so we add that on, plus 40 kilonewtons times meters, and then we have our moment created by our point force at B, which is 1 kilonewton, and let's remember this beam is 8 meters long. So that's in the negative that's in the positive direction, so positive 8 times 1. So let's solve for MD. So moving MD to the other side, we have positive MD now is equal to 40 kilonewtons times meters plus 8. So 48 kilonewtons times meters is our bending moment, our internal bending moment at D. And we've done it. We've figured out our internal forces at the cut we made at D right here. Let's scroll back up. We figured out our internal forces at the cut we made at C right here. And we figured out our unknown forces on our original beam here using the equations of equilibrium. And then we made cuts at each of the points, solved for our internal forces, solved for our internal forces again, and that's it. And that's how you find internal loadings in beams and rods. Thank you for watching. Have a great